And another example we'll do with parameter elimination, which would be example 5. And with the same question, identify the parametric curve. And the curve is given by the pair of equations x equals tangent squared of theta, y equals secant of theta. And we won't impose any, well, actually no, let's do theta is between minus pi over 2 and pi over 2. So here we no longer use the letter t for our parameter. Of course, as I mentioned, we are free to use any letter we like for the parameter in the parametric curve. And we prescribe this specific range to the parameter. So to express one of these variables through the other, well, first we have to pick which one we want to make the independent variable and which is going to be the dependent variable, aka the function. And so if you observe that y, so the dependence, the relation between x and y is since they are secant and tangent, we have the Pythagorean identity relating them. And because we have tangent squared as the equation for x, it will be easier to make x the dependent variable. So let's write this down. It is easier to make x dependent. Let's put it this way: to make x the function of y, not vice versa, because of the square. And what we have to do to relate this is just to use the Pythagorean identity. So we have that secant squared theta minus tangent squared theta equals 1, right? This is the Pythagorean identity. And what we'll do is just replace the expressions in terms of theta by the expressions in terms of x and y. And this gives, since y is secant squared, we get y squared minus x equals 1. And so then after shuffling the terms around, we get that x equals y squared minus 1. If I take this term to the right and this term here to the left, this is what I obtain. And so again, in place of expressing theta through x and then substituting that into the equation for y or vice versa, so in place of what we could do is express theta through y and then plug that into the equation for x. Now we didn't do that because that would be rather tedious. You'd have to look at a composition of an inverse trig function with another trig function. That's not a pleasant thing to look at. So instead, what we do is we use this known identity and express the terms occurring in this identity through the x and y, and thereby we're relating x and y, which gives us the desired dependence. Now, this gives us the shape of this parametric curve, right? But in order to determine the direction of motion along it, so clearly we see that this is a parabola oriented horizontally, but we still need to determine the direction of motion of our particle on it. And so to do that, we need to use this range for theta that we have. And so to use that, we need to translate the range for theta into a range for y, because now y is the independent variable. And so how do we do that? Well, we think about, so when theta is between minus pi over 2 and pi over 2, what are the values for y? So, well, y, for these values of theta, y being secant theta, aka 1 over cosine theta, which values can it take? Well, in this range, cosine theta is positive, and obviously being cosine, it is never bigger than 1. So in this range for thetas, cosine is between 0 and 1. And we are dividing 1 over something in this range, and so this must be bigger than or equal to 1. So the range for y in this parabola is y must be bigger than or equal to 1. And so this completes our process of recognizing this this curve. So we have successfully identified our curve as being a parabola oriented horizontally. Okay, and we know that x equals y squared minus 1, so it's a parabola with a vertex at minus 1, 0. So let's see, this parabola would look like, if this were minus 1, 0 over here, this parabola would look like so. Okay, so this is the entire parabola. So the smallest value for x obviously is minus 1. But now we do not have this entire parabola, we only have values for y bigger than or equal to 1. So here is the the 1 on the y-axis, and so since y is bigger than or equal to 1, you can only take values from this part, and the corresponding piece of the parabola is right here. So everything else is not there, so we have to erase this part. Right, this is not there. These points on the parabola, y squared minus 1, correspond to values of y less than 1. So we only have this part over here. Except that now I see that I have the intercept wrong. So let's see. So this curve. So let me roll back to the complete parabola. So actually I have this picture wrong, I think. Yeah, so actually this point, it lives over here. Yeah, that's precisely the y-intercept. And so now again I have to erase the part of the parabola that corresponds to values of y less than 1. So here are all such values, all such points on the curve, and I only have this part of the parabola. Okay, great. And so I have the shape of my curve. Now let me determine in which way our particle will be moving. So I have that theta is between minus pi over 2 and pi over 2. So when theta is close to minus pi over 2, y is 1 divided by something very small and positive. So y is very large, has very large value, and we are very far that way on our curve. Now, as theta grows from minus pi over 2 to 0, cosine of theta goes from 0 to 1. So cosine of 0 is 1. So cosine goes up to 1, and our particle moves towards this point here. When theta is 0, we have the value for y is 1 over cosine of 0, that's 1. And so this point here with coordinates 0, 1, so this is 0, 1 right here, and so that corresponds to theta being equal to 0. And so after our particle came from infinity towards this point on the curve, then when theta grows from 0 to pi over 2, it works its way backwards all the way to infinity. So this piece of parabola, this piece of horizontal oriented parabola, is covered by our particle twice. So it first comes from infinity to this endpoint and then goes back to infinity as theta keeps growing. And this is how you identify this curve as parabola and determine the specific behavior of the particle whose trajectory this curve is, if you think of the parametric curve as a trajectory of a physical object.